Okay, so we're building up this total. And you know, I asked, well, how do you want to set it up? So I said, okay, we'll go from j equals 1. Set j equals 1 to r, but that doesn't make any sense. The subscripts on j, on theta, yeah, which is the only thing that goes from 1 to m, okay? Don't go from 1 to r, okay? And these are subscripts, and we want to be clear on that. Okay, and then we're probably just going to go from I equals 1 to n, right? Okay? So then what are we going to put in here? Well, we're going to put the moment of inertia of the typical increment, right? Okay? Now, that's mass times r sub I squared, right? Well, what are we going to use for mass? Well, density times area, right? What are we going to use for density? Well, we haven't figured that out yet, but that's really simple. We're just going to call it rho for the moment, or lambda, you know, density, and we multiply by area. What are we going to use for area? Well, we've built this thing up from here down to here, right? It's clear we're going to use Ri star delta theta j delta Ri, right? So it's going to be what? It's going to be mass, which is density times area, and area is this, density is rho, so it's going to be rho times Ri star delta theta sub j delta r sub I. Okay? And that equals what? Or that approaches as
Isn't it mass times Ri star squared?
yeah. Okay. Again, watch me, I'm careless. Okay. So this approaches what? Is Ri, delta Ri's go to 0. Now you got to be careful. All your delta theta j's have to stay less than some number that goes to 0. All your delta Ri's have to stay less than some number that goes to 0. Okay? And I don't want to belabor that point right now.
Won't it be rho r cubed?
Rho what?
R cubed or I?
Oh yeah, that's times then. Okay, now it looks really bad, so I'm going to have to rewrite it, but I'm going to leave it up there right now. Yeah, because your area increment has your Ri star delta theta j delta Ri, which is what I wrote down here, and I didn't write my Ri stars. Okay? Okay, anyhow, this approaches what? Approaches the double integral of rho r squared times r d theta dr. Now I could write that as an r cubed, but I want to be sure we understand that one of those r's is part of your area increment. Okay? Yeah, I should have been more careful when I wrote it up there. Okay? Now, again, what are the limits on this integral? Well, when j goes from 1 to m, what happens to theta?
Goes from 0 to 2 pi.
Yeah. No, very simple question, very simple to answer. If you have your partition written down, you see right away what your limits are. So it's from 0 to 2 pi. And then this is clearly from 0 to r. And there's your moment of inertia. All you got to do is figure out rho. Okay? And rho equals m over IR squared, mass divided by area, because the density is uniform. Okay?
So if you'd go ahead and put R in there. Oh, that's big R.
It's big R. just a constant goes out in front. Rho's
Yeah.
constant,
I
right?
was thinking it would cancel out the r squared.
Yeah, well, yeah. And that's the kind of thing, well, I wouldn't do that because I'm pretty focused on upper versus lower case. After, years, I haven't lost that one yet, but it'll come, it'll go someday. Okay, so you get the idea? Now I leave the rho in here because rho isn't always constant for every object, okay? You have varying densities, and if we had a varying density function, it would vary with r and or with theta, okay? Generally with r. If we had a varying density function, then we wouldn't be able to pull it outside. Okay, so this is a general moment of inertia integral for any circular object. You just have to plug in the density function. Okay? Make sense? So if I give you some density function, you still know what to do. Everything we did works, which is why I didn't originally figure out the density. I wanted to do it for general density. In this case, you have a constant density, so rho comes out, and you just have to integrate. You get r to the 4th over 4 times 2 pi, right? That's going to give you big R to the 4th over 4 times 2 pi. But you're going to have this over pi, and you're going to end up with 1/2 big M R, big R squared. Okay? And that's a moment of inertia of a uniform disk. We'll talk more about the intuitive aspects of that in physics, but that's the way it goes. Okay?